Solo Versace, you copy my style, pop shop in a photo. I took in a smile, fancy chin banging. This video. And here's again my face. It's gonna be cute. So in this video, we're gonna start from the day 11. So that's showing on the show. So the title was title is CCNA following from day 11. Textbook. Okay, let's the first here. What is Prog? You don't know. How is the process used to determine that the methods to take over the next which their destiny. First or roots all of the routing table. Others receive that you can be able to there are two main routing methods. Others used to learn routes, or you can call it dynamic routing. Dynamic routing is a routers use dynamic protocol. All is routing with other we can create their route tables. Google and static routing here admin you can routes.
into the router. A route tells the router, to send a packet to destination X, you should send the packet to next hop Y. And next hop means the next router in the path to the destination. Or if the destination is directly connected to the router, send the packet directly to the destination. Or if the destination is the router's own IP address, receive the packet for yourself, don't forward it. This is how the routing table works. It's a set of instructions like this. To demonstrate routing in this video and the next one, we will use this example network. Actually, in this video, we will only look at one small part of this network. In the next video, we will use the entire network. But first, let me introduce the network. There are 4 routers connected together, and they represent a WAN. WAN stands for Wide Area Network, a network that extends over a large geographical area. For example, each of these 4 routers could be in different cities or even different countries. And then, connected to R1 and R4, there are 2 LANs, Local Area Networks. I'm only showing one PC at each LAN, but let's say each of these LANs is a different office in a different city. So really there are more hosts in each LAN. R2 and R3 probably should have their own connected LANs too. But just to keep the diagram a bit cleaner, I'm not showing them here. Now let's look at the IP addresses each device will be using. For this LAN connected to R1, the network is 192.168.1.0/24, and R1's G02 interface IP is .1, and PC1's IP is .10. Then this WAN connection between R1 and R2 is 12.0/24. R1 G01's IP is .1, and R2 G00's IP is .2. This WAN connection between R1 and R3 is 13.0/24, with R1 G00 as .1 and R3 G00 as .3. The WAN connection between R2 and R4 is 24.0/24, with R2 G01 as .2 and R4 G00 as .4. Then the final WAN connection between R3 and R4 is 34.0/24, with R3 G01 as .3 and R4 G01 as .4. Then the LAN connected to R4's G02 interface is 192.168.4.0/24, with R4 G02 as .4 and PC4 as .10. Notice that I made all of the router IP addresses the same as their name. All of R1's IP addresses are .1, R2's IP addresses are .2, R3's are .3, etc. Don't expect IP addresses like this in real network, but in lessons and labs, I will often use simple addressing schemes like this to make it easier to understand. In the next video, we will configure static routes on the routers to allow PC1 and PC4 to communicate with each other over the network. This video will focus on 2 types of routes automatically added to a router's routing table, not dynamic routes or static routes. Okay, before looking at since that's the router we'll be focusing on in this video. First, I configured its G00 interface with 168.13.1, 255.255.255.0, and then enabled it with no shutdown. Then I configured G01's IP address. Notice that while I was still in interface config mode for G00, I used the interface G01 command directly, without returning to global config mode first. There is no need to use exit to return to global config mode before entering interface G01. You can use the interface G01 command directly from interface config mode. I then configured G02 as well. To confirm, I used show IP interface brief, and you can see the IP addresses I just configured. Of course, I configured the other router's IP addresses too, but for the sake of time, I won't show them here. As I said, in this video, we'll just focus on R1. Now let's take a look at R1's routing table. The command is show IP route. It displays the router's routing table. And here is the output. There are two main sections to the output: the codes at the top and the actual routes at the bottom. The codes legend in the output of show IP route lists the different protocols which routers can use to learn routes, as well as the codes that represent them in the routing table. I've highlighted two in blue here. The first is L, which means local. This code is used for routes to the actual IP address configured on the router's interface, and these routes will have a /32 mask. If you look at the routes below, notice there are 3 routes with L that I've highlighted in blue, one for each of R1's interfaces. Then there is the C code, which means connected. These are routes to the network the interface is connected to, with the actual net mask configured on the interface. Notice there are also 3 routes with the C code in the output below. So even though we haven't configured any routes yet on R1, it already has 6 routes. When you configure an IP address on an interface and enable it with the no shutdown command, 2 routes per interface will automatically be added to the routing table: a connected route and a local route. Earlier, I mentioned that there are 2 main types of routing: dynamic routing and static routing. These connected and local routes, however, are neither. They are simply added automatically when an interface is configured. These are the routes we will focus on in this video. Okay, let me explain these routes in more detail. So, I've highlighted 2 of the routes. One connected route to 192.168.1.0/24, and one local route to 192.168.1.1/32. So a connected route is a route to the network the interface is connected to. R1G02's IP is 192.168.1.1/24. What do the red and blue numbers mean here? Well, because it's a /24 address, the first 24 bits, the first 3 octets, are the network portion of the address. I've highlighted that portion in red. Then the last 8 bits, the last octet, is the host portion of the address, and I've highlighted it in blue. When you change that host portion to all zeros, the result is 192.168.1.0/24. And notice, that's the destination of that connected route. It's a route to that network. So this provides a route to all hosts in that network. For example, 192.168.1.10, etc. Any address in that .0/24 range. Look back up at the routing table, and notice that the route says 192.168.1.0/24 is directly connected, gigabit Ethernet 02. So, R1 knows, if I need to send a packet to any host in that network, I should send it out of G02. Okay, that's the connected route. Next, let's look at the local route in more detail. A local route is a route to the exact IP address configured on the interface. A /32 net mask is used to specify the exact IP address of the interface. /32 means that all 32 bits are fixed. They can't change. So, even though R1's G02 is configured as 192.168.1.1/24, the local route is to .1/32, which specifies only that single address. It doesn't include 192.168.1.2, for example. So, with this route, R1 knows, if I receive a packet for this IP address, the message is for me, to my own IP address. Just to make things clearer, let me show it like this. /24 means that the net mask is 255.255.255.0. The first 24 bits of the net mask are all 1, so each octet is 255. These bits are fixed, they can't change. However, the last 8 bits, the last octet, are not fixed. They can be any number. So the route for 192.168.1.0/24 matches 192.168.1.0 to 192.168.1.255. That means that if R1 was fixed, now to make things clearer, let me show it like this. Slash 24 means that the net mask is 255.255.255.0. The first 24 bits of the net mask are all 1, so each octet is 255. These bits are fixed, they can't change. However, the last 8 bits, the last octet, are not fixed. They can be any number. So the route for 192.168.1.0/24 matches 192.168.1.0 to 192.168.1.255. That means that if R1 receives a packet with a destination in that range, it will send the packet out of the G02 interface. Let's see some examples. A packet with a destination IP address of 192.168.1.2 is a match, because the IP address begins with 192.168.1. Because it's /24, the first 3 octets have to match. So R1 would send the packet out of G02. 192.168.1.7 would also match this route, so R1 would forward the packet out of G02. Likewise, 192.168.1.89. A packet destined for 192.168.2.1, however, does not match. It cannot use this route, because the destination does not begin with 192.168.1. So what would R1 do with this packet? It would send the packet using a different route, or drop the packet if there is no matching route. The term match is very important, and I will use it a lot in this video and others. Route matches a packet's destination if the packet's destination IP address is part of the network specified in the route. Using an example on the right, 192.168.1.2 is part of the 1.0/24 network, so the route matches the destination IP. Destination 192.168.2.1 not part of that network, so the route does not match that destination IP. Now, the local route to 192.168.1.1/32 is simple. Because it's /32, all bits of the net mask are 1, so it's 255.255.255.255. All of these bits are fixed, they can't change. So, 192.168.1.1/32 matches only destination 192.168.1.1, no other IP addresses. Okay, we looked at those connected and local routes that were automatically added to R1's routing table when we configured IP addresses on its interface. Now let's look at another fundamental concept, route selection. So R1 has a connected route to 192.168.1.0/24 and a local route to 1.1/32. Let's say R1 receives a packet and the destination IP is 192.168.1.1. Can you see the problem here? A packet destined for 1.1 is matched by both routes, 192.168.1.0/24 and .1/32.
For itself.
So which route will R1 use for a packet destined for 1.1? Will it send the packet out of G02, or will it receive the packet because the packet is for R1 itself?
Receiver.
The answer is, it will choose the most specific matching route. So I explained what a matching route is. Let's see what most specific means. Route to 192.168.1.0/24 includes 256 different IP addresses, from 192.168.1.0 to .255. On the other hand, the route to 1.1/32 includes only one IP address, 192.168.1.1. It specifies just one IP address, not 256 different IP addresses. So, this route is more specific than the /24 route. So, when R1 receives a packet destined for 192.168.1.1, it will select the route to 1.1/32. So, R1 will receive the packet for itself rather than forward it out of G02. That's the purpose of local routes. They tell the router, keep the packet, don't forward it. This means R1 will de-encapsulate the packet and look at the contents inside, because the contents are addressed to R1.
Local route. Keep the packet. Don't forward.
1 itself. So, to summarize, the most specific matching route means the matching route with the longest prefix length. Both parts of that statement are important. The route must match the packet's destination, and it also must have the longest prefix length out of all the matching routes. That is the route that the router will use for the packet. Now let me point out these statements here in the output of show IP route on R1. You might have noticed them and wondered what exactly they mean. The top one says 192.168.1.0/24 is variably subnetted to subnets to masks. What exactly does that mean? Well, first of all, it's important to know that these three lines are not routes. They mean the following. The first line, 1.0/24 is variably subnetted to subnets to masks, means that in the routing table, there are two routes to subnets that fit within the 1.0/24 class A network with two different subnet masks, those being /24 and /32. The other two mean the same thing for their.
These three lines are not route. They mean the following. 192.8.1 variably subnetted. That's routing table. There are two routes. Routing table. There are two routes. Subnet that fit within the network. Two different 192.168.12.0/24 variably subnet mask. In the routing table, there are two routes fit within the 192.168.12.0/24 class C with two different networks, /24 and 32. 192.168.13.13.0/ variably two subnets the mask routing table within with two different netmasks, /24 and 32. Network is have connected directly within 100 and is still iPad and connected. And this comes this magic. It will receive from for the error forward to its parts. Error forward to isolation 0 to 100.
Respective networks. To really understand these statements, you have to understand what a subnet is. but we haven't covered subnets yet in the course. We will cover subnetting soon, in another video. For now, I just wanted to point out that these 3 lines are not routes, so you don't get confused by them. Generally, you can ignore this output in the routing table and just focus on the routes themselves. Now let's look at a few examples to practice route selection. R1 receives a packet destined for 192.168.1.1. Looking at its routing table, which route will it select for this packet? And what will it do with the packet?
Have 192.168. For and then from R1 0.
You will answer yourself. So we have to find the most specific matching route in the routing table. This first packet is destined for 192.168.1.1, and when R1 checks its routing table, it will see that the most specific match is this one, to 192.168.1.1/32. It is a local route, so R1 will receive the packet for itself. Note that this packet matches 2 routes in the routing table, the route for 1.0/24 and the route for .1/32. But the /32 route is more specific, so it will be selected. Here's another example.
Forward the packet to destination. And 13. It will forward or receive will be the interface with G0 here. Is the 192.168 change the IP become so it will be forward to 00. It's not R1 interface. Will be forward. Check. Okay, real quick. Check.
Packet 2 has a destination IP address of 192.168.13.3. Which route will R1 select for this packet? What will it do with the packet? The most specific matching route, actually the only matching route for this packet, is this connected route to 13.0/24. So R1 will send the packet to the destination, which is connected to the G00 interface. Here's a third packet.
The packet 3. Packet 3 contains destination IP that has 192.168.1.244.45. So for this packet, it will send to G02 interface because it contains 192.168.1.0/24 that has that range. Because that range of 192.168.1.0 is 1.1 to 245 subnet. So you will be forward the packet through G02.
Destination IP 192.168.1.244. What will R1 do with this packet? The only matching route is this one to 1.0/24, so R1 will use this route to forward the packet. It's a connected route, so R1 will send the packet to the destination, which should be connected to that interface. And here's a fourth packet.
So the fourth packet here, it contains destination IP 192.168.12.1. So this IP will be forward through G01 R1's interface. No. For this IP address 192.168.12.1 will be received by R1 itself because it is connected to the local route. So the 12.1 is most specific or the least prefix of this episode. The R1 will receive for itself.
Destined for 192.168.12.1. What will R1 do with this packet? There are two matching routes, but the most specific one is this local route for 192.168.12.1/32. So R1 will receive the packet for itself. Okay, let's do one more practice question. Packet 5.
Packet 5 contains 192.168.4.10. So for this IP subnetting that we got and we configured, we didn't have that specific routes that we configured that matching that IP address 192.168.4.10. I mean the network part 4 didn't have that configured. So the R1s will be drop the packet.
5 is destined for 192.168.4.10. What will R1 do with this one? Because there are no matching routes in the routing table, R1 will have to drop this packet. Unlike switches, which flood frames if they don't know where the destination is, routers do not. Routers never flood packets. If the router doesn't have a route to the packet's destination, it will drop the packet. Okay, now let's try to review everything in this video in one slide. This will be just a wall of text. Hopefully, it will help you review what we learned in this video. Routers store information about destinations they know in their routing table. It's like a switch's MAC address table, but of course it functions differently.
This one. routers. So, mm, about initial they know in their routing but
And when they receive packets, they look in the routing table to find the best route to forward the packet. Each route in the routing table is an instruction. A route says, for each destinations in network X, send the packet to next hop Y, which is the next router in the path to the destination. Now, on most routers, they will have lots of routes like this. For each destination X, send packets to next hop Y. However, in this video, we didn't actually look at this kind of route. We looked at connected and local routes. Connected routes say, if the destination is directly connected to this router, send the packet directly to the destination. Or if the destination is your own IP address, if the destination is
uh,
receive the packet for yourself. This is how a local route works. Anyway, the point is that the routing table is a set of instructions for the router, telling it how to forward packets. In the next video, we will look at how next hops work when we learn about static routes. When you configure an IP address on an interface and enable the interface, two routes are automatically added to the routing table. The first is a connected route, indicated with code C in the routing table. It is a route to the network connected to the interface. For example, if the interface's IP is 192.168.1.1/24, the connected route will be to 1.0/24. I'm repeating the point above, but it tells the router to send a packet to a destination in this network, send it out of the interface specified in the route. Then, the other kind of route is a local route, indicated by code L in the routing table. It's a route to the exact IP address configured on the interface. So, if the interface's IP is 192.168.1.1/24, the route will be to 1.1/32. A /32 netmask is used to specify just the one IP address. This tells the router, packets to this destination are for you, and you should receive them for yourself, not forward them. Okay, we also talked about how routes match destinations. The route matches a destination if the packet's destination IP address is part of the network specified in the route. For example, a packet to 192.168.1.60 is matched by a route to 1.0/24, but not by a route to 0.0/24. Now, if a router receives a packet and it doesn't have a route that matches the packet's destination, it will drop the packet. This is different than switches, which flood frames if they don't have a MAC table entry for the destination. Final point. If a router receives a packet and it has multiple routes that match the packet's destination, it will use the most specific matching route to forward the packet. And the most specific matching route, the matching route with the longest prefix length. This is different than switches, which look for an exact match in the MAC address table to forward frames. Frame's destination MAC address must be the exact same as the entry in the MAC address table. There's no concept of most specific match in switches. Okay, so that was a summary of this video. Hopefully it helps you review what you learned in this video, because this is important fundamental information. Here are the general topics we covered in this video. I introduced the concept of routing, the process routers use to determine the path that IP packets should take over a network. We examined the routing table on a Cisco router, specifically looking at connected and local routes, which are automatically added to the routing table to configure an IP address on an interface. And we also looked at routing fundamentals, how routers select which route to use to forward a particular packet. We do that by looking for the most specific matching route in the routing table. Now, there's still lots more to cover about routing.
What is routing? Routing is protocol in the network. So when the router receives the packet, it will choose what the next hop or next path is. So the router has a routing table too. So in the routing table, it stores all the routing all the routing tables are routing tables. So the routing table on Cisco routers contains the connected and local routes. Connected routes means the network part the IP address. The local routes is the most specific IP address that you can figure on that interface. For example, when we configure an IP that has 192.168.1.0, the connected part is the 192.168.1.0 to 192.168.1.245 for the host portion. For the local routes, more specific routes. So when the packet that has the destination for your specific IP address that you configure on your interface, example 192.168.1.1, it will be sent to router, not forward the packet to connect section. So the router will receive the packet, not to the connected.
And in the next video, we'll dig deeper into the topic by looking at static route. Okay, now let's move on to the quiz to test your understanding of the concepts we covered in this video. Here's quiz question 1. The IP address configured on a router interface will appear in the routing table as what kind of route?
The IP address configured on a router interface will appear in the routing table as what kind of route? Local route.
Pause the video now to select the best answer. Okay, the answer is C, local. You configure an IP address on an interface, 2 routes are automatically added to the router's routing table, assuming the interface is enabled. Note that if the interface is shut down, the routes won't appear. Anyway, the routes that are automatically added are a connected route, the network, and a local route, to the exact IP address configured on the router interface. Okay, let's go to question 2. Examine R1's routing table. What will it do when it receives a packet destined for 192.168.3.25? Pause the video now to examine R1's routing table and select the best answer.
Examine R1's routing table. What will it do when it receives a packet destined for 192.168.3.25? So for the connected, for the IP address that we see that configure on these routers are 192.168.1.0, 192.8.2.0, and 2.68.13.0. So it has the answer is it will drop the packet because it has no matching network address that we configure on that device. Instead, we have .1, .2, .13, and no .3 configured here, so it will drop the packet.
Okay, the answer is B. It will receive the packet for its...
S1 Vietnam, Vietnam, kedua Vietnam, 13 Vietnam. Wish. Reliability domain from
So, packets destined for 3.20. Which of the following statements about the behavior of routers and switches are true? Select 2. Pause the video now to select the best answer.
Which of the following statements about behavior of routers and switches are true? So we will check one by one. Routers, 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 routers flood packets with an unknown destination. No, it's wrong because routers never flood the packets. Routers will either drop forward the packet or flood the packet. B. Switches flood frames with an unknown destination. The switches flood frames. Routers drop packets with an unknown destination. The switches drop frames with an unknown destination. The answer is B and C.
Okay, the answers are B and C. Switches flood frames with an unknown destination. Those are called unknown unicast frames. Routers, on the other hand, never flood packets. Instead of flooding packets with unknown destinations, the router simply drops them. Okay, let's go to question 4. Which two types of routes are automatically added to the routing table when you configure an IP address on an interface and enable? Pause the video now to select the best answer.
Which two types of routes are automatically added to the routing table when you configure an IP address on interface and enable the? The answer is local route and connected.
C and Okay, the answer is A, C and L. As shown in the show IP route output on the right, C stands for connected and L stands for local. These two routes are added when you configure an IP address on an interface and enable it. Okay, let's go to question 5. Examine R1's routing table below. If R1 receives a packet destined for 10.0.1.23, how many routes match that destination? And which is the most specific matching route? Pause the video now to examine the routing table and select the best answer.
Examine R1's routing table below. If R1's receives a packet destined for 10.0.1.23, how many routes match that destination? And which is the most specific matching routes? So as we can see here, we can configure IP address is 10.0.0.0, 10.0.0.0, and 10.0.1.0. And as we can see in the 10.1.0, 10.0.1.0/24, it has two routes, the connected route and local route. So it match the two routing, match the 10.1.1, 10.0.1.0/24, and 10.0.1.23/32 as its most specific IP. So the answer is C.
Okay, the answer is C. There are two matching routes, 10.0.1.0/24 and .23/32. And the most specific matching route is the route to .23/32, so that route will be selected. It's a local route, so that means R1 will receive the packet for itself. It won't forward it to another device. Okay, that's all for the quiz and this video. I hope it was helpful. Thanks for watching. Before finishing,
Now we added to Anki flashcard, and gonna practice to answer the textbook question from the YouTube video. Open my Anki, so as you can see here on my flashcard that has a do. I'm gonna have so much time to configure this to answer this. So we're watching the day 11 part 1 flashcard. Like that and studying. A route is the route to actual IP address configured on an interface. Local. Local. Good. What will a router do if none of its routes match a destination IP address? What will the router do? Router will route. Show the routing table. Show IP route. Most specific matching route pulls the matching route with the um, with the most highest prefix. So the /32 longest prefix, which two routes are automatically added to the routing table when you configure an IP address on a page. So the routes that automatically added is the route that automatically added are local routes and the connected route. What does code C in the routing table mean? Code C, the code C means connected. So the connected routes means the connected route means the network portion of an IP that we configure. Route is a route to a network the interface is connected to. Connected route. Local routes use a prefix length of /32. What prefix length do connected routes use? /24. No. Depends what subnet mask do you use or what subnetting do you use on your IP. So when you configure an IP on a router, it will automatically switch to that IP address that you configure. So it depends. But for the latest video that we watch, it /24. Okay. Prefix /configure on the interface. So it's not /24. Routers store routes to all of their known destinations in the routing table. The next router in the path to the destination is called the next stop. What does code L in the routing table mean? Local routes. A route is added to the routing table by a protocol OSPF that allows routers to communicate with each other and share routing information. Dynamic, because the OSPF is a dynamic host configuration protocol. If a packet's destination IP is matched by multiple routes, which route will the router select? The route, router will select the most specific routes, so the longest prefix by multiple routes, the most specific or the longest prefix. When routers receive packets, they look in to find the best route to forward the packet. Routing table. A route is manually configured by a network engineer or admin. That it. Congratulations, you have finished this step for. Chill for 5 minutes. I'm gonna do that. What's that? Automotive technique. So I will be sharing top of 5 minutes. Met everyone. Confiado corazón. Ah, corazón espinado. Ah, corazón espinado. Ah, espinado. Corazón espinado. Corazón espinado. Corazón. Espinado. Corazón espinado. Anjing, anjing.
Good time. Good time. Right. Too much.
Right, let's continue to our. So the next part will be the routing fundamentals day 11 part 2. Hi. So it was the static routing day 11 part 2. Yeah. Let's get it in.
Welcome to Jeremy's IT Lab. This is a complete course for the CCNA, Cisco Certified Network Associate exam. This video, we will cover static routing, a very important topic to understand for the CCNA exam. In the previous video, we looked at the basics of routing, how routers decide where to forward packets. And we looked at two types of routes, local routes and connected routes. Those routes are automatically added to a router's routing table when you configure an IP address on the interface. Local routes provide a route to the router's own IP address. And connected routes provide a route to the network the interface is connected to.
Network.
However, if you want the router to be able to send traffic to destinations that aren't directly connected to the router itself, local and connected routes aren't enough. Today's topic, static routes, enable routers to send packets to remote destinations that aren't directly connected to the router itself. Here's what we'll cover in this video. First, we'll briefly review connected and local routes, while looking at the rest of the network topology I introduced in the last video. Then I will introduce static routes, and how we can use them to instruct routers about how to forward packets. And of course, we'll see how to configure static routes in the CLI of Cisco routers. Unlike connected and local routes, static routes are not automatically added to the routing table and must be manually configured. Finally, I will also explain the concept of default routes. So first up, let's review connected and local routes by configuring IP addresses on the routers and checking their routing table. In the last video, I showed R1. So for this video, let's start from R2. I configured IP addresses on G00 and G01 and enabled both interfaces. Remember, if an interface is disabled, the connected and local routes for that interface won't appear in the routing table. Now, before I show the routing table, I want you to think about what routes there will be in the routing table. There should be one connected route and one local route per interface, so a total of 4 routes. Remember, these routes are added automatically when you configure IP addresses on router interfaces. So what will the destination of each route be? Well, the connected routes are routes to the networks R2's interfaces are connected to. So there should be one route to 192.168.12.0/24 and one route to 24.0/24. And then the local routes are to the exact IP addresses configured on R2's interface. So there should be a route to 192.168.12.2/32 and a route to 24.2/32. Okay, here are the routes. Note that for the sake of space, I'm not showing all of the different codes listed at the top of the output. Remember, C means connected and L means local. Anyway, as expected, R2 has 2 connected routes, one to 12.0/24 and one to 24.0/24. Also, it has 2 local routes, one to 12.2/32 and one to 24.2/32. So to summarize, R2 knows how to reach its own IP addresses and destinations in its connected network, but it doesn't know how to reach destinations in remote networks. By remote networks, I mean networks not directly connected to R2. So, R2 knows how to reach destinations in the 192.168.12.0/24 and 24.0/24 networks, including its own IP addresses in those networks. But it doesn't know how to reach any of the other networks in the topology. If R2 receives packets destined for hosts in these other networks, it will have to drop them. R2 doesn't know where it should send them. here's R3's configuration. 192.168.13.3/24 on its 00 interface, and 34.3/24 on G01. So which routes will it have in its routing table? As you should know by now, it has 2 connected and 2 local routes. So like on R2, R3 knows how to reach its own IP addresses. Those are the local routes, and destinations in its connected networks. Those are the connected routes. It doesn't know how to reach destinations in remote networks. So
for the remote network that will not covers and not learned by the R3 is 192.168.1.0, 192.168.12.0, 192.168.1.24.0, and 192.168.4.
It knows how to reach 193.168.13.0/24, including its own IP of 13.3/32, and it also knows 34.0/20, including its own IP of 34.3/32. It doesn't know how to reach any of the other networks. So, for example, if it receives a packet and the destination is PC4's IP address, 192.168.4.10, R3 wouldn't be able to forward the packet. It would have to drop it. And here's R4's configuration. Note that R4 has 3 interfaces in use. So how many routes will it have in its routing table? The answer is 6. 3 connected and 3 local. Same as R2, R3, and also R1, which we looked at in the previous video. R4 knows how to reach its own IP addresses and destinations in its connected network. Not how to.
4.4 and 4.4 literally
reach destinations in remote.
R4 knows how to reach its own IP address and destination in its connected network, but it doesn't know how to reach destination.
These are the networks it knows, and these are the ones it doesn't. For example, if it receives a packet
12,
it destined for PC4, 192.168.4.10, it has a route to 4.0/24, so it would be able to forward the packet to PC4. However, if it receives a packet destined for PC1, 192.168.1.10, it doesn't have any routes that match that destination IP, so it would have to drop the packet. So, all of these routers have connected and local routes. Now let's start looking at how we can configure them to allow PC1 and PC4 to communicate. Notice that I've colored the interface labels for each device, and also added interface names for PC1 and PC4. PC1 and PC4 are Linux hosts, and their default interface name is ETH0, Ethernet 0. These colors will make things easier to understand as I demonstrate how packets move through the network. So first we are going to look at the concept of default gateway. End hosts like PC1 and PC4 can send packets directly to destinations in their connected network. PC1 is connected to 192.168.1.0/24, so it can directly communicate with other hosts in that network. And PC4 is connected to 4.0/24, so it can directly communicate with hosts in that network. However, to send packets to destinations outside of their local network, they must send packets to their default gateway. Gateway is an old term for router, so it means default router. So these are the configs on PC1 and PC4. Linux, the interface configurations are stored in a text file that you can edit. On PC1, for example, there is the line address 192.168.1.10/24, which configures the IP address as 1.10 with the prefix length of /24. And below that is the default gateway configuration, gateway 192.168.1.1. So to send packets to destinations outside of its local network, PC1 will send packets to R1. The default gateway configuration is also called a default route. Basically, it's a route to O.O.O.O/O. All netmask bits are set to 0. None of the bits in the address are. O.O.O.O/O includes all addresses from O.O.O.O to 255.255.255.255. It's a route that includes everything. Remember the concept of most specific matching route in the previous video? Well, the default route is the least specific route possible, because it includes all IP addresses. O.O.O.O/O includes over 4 billion IP addresses. On the other hand, a /32 route, like a local route, is the most specific route possible. It specifies only one IP address. For example, 192.168.1.1/32 specifies only one IP address. So the default route says, if there aren't any more specific matches for this packet, don't drop it. Send it via this route instead. Later, we'll see how to configure a default route on a Cisco router and what it can be used for. But for now, just understand how it works for end hosts like PC1 and PC2. End hosts usually have no need for any more specific. They just need to know, to send packets outside of my local network, I should send them to my default gateway. So if PC1 wants to send a packet to PC4, the source IP address in the IP header is 192.168.1.10, PC1's IP, and the destination IP is 4.10, PC4's IP. Now here's a major point. What will the source and destination MAC addresses be in the Ethernet header? This is where you can start to really understand the role of Layer 2 and Layer 3. Layer 3, PC1 wants to send a packet to PC4. So the destination is PC4's IP, 192.168.4.10. However, it has to first forward this packet to its default gateway, R1. So it will encapsulate the packet in a frame, and the destination MAC will be R1G02's MAC address. Now, how does it know R1G02's MAC address? To learn it, PC1 will first send an ARP request, 192.168.1.1, R1G02's IP address. I will show this part of the process in more detail in the next part of the course, called Life of a Packet. To keep things a bit simpler in this video, let's just assume each device already knows its neighbor's MAC address. I won't show all of the ARP exchange. So PC1 sent that frame to its default gateway, R1. R1 receives the frame. It will de-encapsulate, meaning it will remove the Layer 2 header and trailer and look at the inside packet. It will then check the routing table for the most specific matching route. It has to make a decision about what it will do with this packet. So here is R1's routing table at the moment, just connected and local route. Do any of these routes match the destination IP of the packet? No, R1 has no matching routes in its routing table. So what will it do with the packet? It has no choice but to drop it. In its current state, R1 doesn't know how to properly forward the packet. Forward it, R1 needs a route to the destination network, 192.168.4.0/20. Remember, routes are instructions. R1 needs a route to say, send a packet to destinations in network 192.168.4.0/24, forward the packet to next hop Y. Now we know the destination, 4.0/24 network. What should be the next hop? What is the next router in the path to the destination? Actually, there are two possible paths that packets from PC1 to PC4 can take. One is the path via R3, PC1 to R1 to R3 to R4 to PC4. The other path is the one via R2, PC1 to R1 to R2 to R4 to PC4. In this video, we will use the path via R3, not the path via R2. So we won't actually use R2 much in this video. The reason I included R2 in the diagram is that I wanted to demonstrate that there are multiple paths to the destination. You can choose which one the routers should use. Now, it is possible to configure the routers to use these multiple differently. Instead of choosing one path, they can load balance between path 1 and 2. That means some packets will Take path 1, some will take path 2. Or they could, for example, use path 1 as the main path and path 2 as a backup path. You will learn about these techniques later in the course. This video, we will only use path via R3. Now, to ensure PC1 and PC4 can communicate with each other, not just R1 that needs another route. Each router in the path needs two routes. A route to 192.168.1.0/24, PC1's network, and a route to 4.0, PC4's network. This ensures two-way reachability, which means that PC1 can send packets to PC4, and PC4 can send packets to PC1. If, for example, all routers had routes to 192.168.4.0/24, not 1.0/24, PC1 would be able to send packets to PC4, but PC4's replies wouldn't be able to reach PC1. R4 would drop the reply, because it would have no route that matches destination 192.168.1. So, we want two-way reachability. It's worth noting that routers don't need routes to all networks in the path to the destination. For example, R1 doesn't need a route to 192.168.34.0/4. Just needs to know, send packets to 4.0/4. I should send the packets to R3. R3 will take care of the packets after that. And likewise, R4 doesn't need a route to 192.168.13.0. R4 just needs to know, send packets to 1.0/24. I should send the packets to R3. R3 will take care of the packets after that. Okay, continuing on. R1 already has a connected route to 1.0/24, and R4 already has a connected route to 4.0. However, the other routes must be manually configured in static routes. Before we get into actually configuring static routes, let's plan out the routes we will configure. Here's a chart of the routes R1, R3, and R4 need to allow PC1 and PC4 to communicate with each other.
In this table, we see the R1's destination that says 192.168.10/24. The next hop is 8 as connected, and R1 is 192.168.4.0/24. The next hop will be E00 R3 2.168.13.3/24.
In blue,
For the R3 destination 192.168.1.0/24, the next hop will be 00 R1 192.168.13.1/24, and R3 192.168.4.0/24. will be 192.168.34.4/24 through G01. And for the R4 destination that has IP 192.168.1.0/24, the next hop will be on G01 R3 that has 192.168.34.3/24.
Are R1 and R4's connected routes. Note I listed the next hop as connected. Then in red are the static routes we have to configure. I will show the answers, but before that, I want you to pause the video and think about what the next hop IP address should be for each route. Let's check. For R1 to send a packet to the 4.0/24 network, what is the correct next hop IP address? Remember, we're using the path via R3 for this, not the path via R2. The answer is 192.168.13.3. The IP address of R3's G00 interface. R1 has a connected route to 192.168.13.0/24, so it knows how to reach 13.3. It can then use that IP address as a next hop, send packets toward the 4.0/24 network. Okay, next one. What next hop IP should R3 use? Send packets to the 192.168.1.0/24 network. The answer is 192.168.13.1, R1's G00 interface. And how about 4.0? It should send packets to 192.168.34.4, R4's G01 interface. Finally, what next hop should R4 use? Send packets to the 1.0/24 network.
R3 G01.
The answer is 192.168.34.3, IP address of R3's G01 interface. Okay, we planned the static routes we need to configure. To allow PC1 and PC4 to communicate with each other over the network, let's configure these static routes on R1, R3, and R4. First up, let's configure R1's routes to 192.168.4.0/. Here is the format of the
IP route
from global config mode, IP route, followed by the destination network IP, netmask, next hop IP. So for R1's route to the 4.0/24 network, command is this: IP route 192.168.4.0, 255.255.255.0, 192.168.13.3. That's it. Fairly simple. I then checked R1's routing table. Notice I highlighted the code for static route, S, as you might have guessed. And I've also highlighted the route itself in the. Notice in square brackets there are two numbers, 1/0. What do those numbers mean? They are the route's administrative distance metric. We will cover these concepts later in the course. Don't worry about their meaning. I'm just pointing them out in case you're curious what those numbers are. Okay, that's all we have to configure on R1. It now knows that, to reach PC4's network, it should forward packets to 192.168.13.3, R3. Next up, R3. It needs two routes, one to 1.0/24 and one to 4.0/24. Format of the command is the same as.
So static route configuration for the R3 through to reach 192.168.1.0 and 4.0. The commands for the syntax will be IP route 192.168.1.0 13.1, and for the 4.0/24 will be 192 IP route 192.168 255.4.0, 255.255.0, 102.168, 34.4.
On our web. If you can, pause the video and try to figure out the correct commands on. Here is the route to the 192.168.1.0/4 network. R1 as the next hop. Here is the route to 4.0/, with R4 as the next. And then I checked R3's routing table too. Again, you can see both routes there with their next hop IP addresses. To reach 192.168.1.0/24, send packets to R1. To reach 4.0/24, send packets to R4. And finally, let's configure R4's route to the 192.168.1.0/24 network.
IP route 192.168.1.0, 255.255.0, 192.8.34.3.
Again, try to pause the video and figure out the correct command if you can. Here is the answer. IP route 192.168.1.0, 255.255.255.0, 192.168.34.3, using R3's G01 interface IP address as the next hop. And here is R4's routing table now. So, we have now configured all of the static routes necessary for PC1 and PC4 to communicate. Let's test it out and see if they can actually communicate with each other. Test it out, I pinged from PC1 to PC4, and the ping was successful. As I've highlighted, it says 5 packets transmitted, 5 packets received, 0% packet lost. If the ping is successful, that means there is two-way reachability. PC1 can reach PC4, and PC4 can reach PC1. If PC1 could reach PC4, and PC4 couldn't send replies back to PC1, ping wouldn't work. So the configurations were successful. Now, let me briefly show how a packet from PC1 to PC4 is encapsulated, de-encapsulated, and re-encapsulated in different frames as it travels through the network. We will examine this process step by step in the Life of a Packet video coming up soon, but this is just a preview. You don't have to think too much about the process. As you saw earlier, when PC1 sends a message to PC4, layer 3 destination is PC4's IP address, 192.168.4.10. However, at layer 2, the destination is PC1's default gateway, which is R1's G02 interface. Now R1 has the packet, and it's R1's job to forward it to the next hop. To do so, it encapsulates the packet in a new Ethernet frame. This time, the destination of the frame is the next hop's MAC address, so the MAC of R3's G00 interface. Now R3 has the packet and must forward it to the next hop. To do that, once again encapsulates the packet in a new Ethernet frame, and the destination of that frame is the MAC of R4's G01 interface. Now R4 has the packet, and since it's directly connected to the destination network, it can forward the packet to PC4. It does that by encapsulating the packet in a frame with PC4's MAC as the destination. This is the only time in the journey that the destination IP and MAC are of the same device. Destination IP is PC4's IP, and the destination MAC is PC4's MAC also. This process is very important to understand. As I said, we will cover it step by step in another video. For now, just understand that the source and destination IPs of the packet not change throughout the journey. Each time the packet is de-encapsulated and re-encapsulated, the source and destination MAC addresses are different. Okay, now I want to introduce another option when configuring static routes. We haven't configured any routes on R2 yet, so I'll just use it for this demonstration. When configuring static routes, instead of configuring a next hop, you can configure an exit interface instead. That means you specify which interface this router should send the packets out of, rather than telling it the actual IP address of the network. For example, if R2 wants to send packets to the 192.168.1.0/24 network, it should send the packets to R1. What interface should R2 send packets out of to reach R1? G00, because that interface is connected to R1. So here's the command. IP route 192.168.1.0, 255.255.255.0, G00. You can type out the whole interface name if you want, or just a shortcut like G00 is fine. Now, before we check the routing table, there is one more option. You can specify both the exit interface and the next hop. So if R2 wants to send packets to the 192.168.4.0/24 network, it should send packets to R4. And which interface should it send packets out of to reach R4?
G01 192
G01, because it's connected to R4. What is the next hop IP address? It's 192.168.24.4, the IP of R4's G00 interface. So here's the command. IP route 192.168.4.0, 255.255.255.0, G01, 192.168.24.4. Okay, and here is R2's routing table now. You can see how each route is displayed. Interesting point is that when you specify only the exit interface of the static route, it says the destination network is directly connected. Look at the route I've highlighted in blue. 192.168.1.0/24 is directly connected. That network is not directly connected to R2, but that's how it displays in the routing table when you configure only the exit interface. Static routes in which you specify only the exit interface rely on a feature called proxy ARP to function. This is usually not a problem, but generally you can stick to specifying a next hop only for both exit interface and next hop. Neither configuration method is necessarily better than the other. Just use whichever you prefer. Note that proxy ARP is beyond the scope of the CCNA. I won't spend time explaining it here. However, you should know that when configuring static routes, you can specify the next hop, exit interface, or both. Okay, for the final topic, I'll introduce how to configure a default route on a Cisco router. I introduced the concept of default routes when explaining how a PC's default gateway works, but let's review. A default route is a route to O.O.O.O/O. /0 means that all bits of the net mask are 0. So none of the bits of the address are fixed. They can all change to be either 0 or 1. So O.O.O.O/O is the least specific route possible. It includes every possible destination IP address. If the router doesn't have any more specific routes that match a packet's destination IP address, the router will forward the packet using the default route. So a default route is often used to direct traffic to the internet. In the network below, R1 is connected to R2 and R3, which are other routers owned by the same business. More specific routes are used for destinations in the internal corporate network, such as destinations connected to R2 and R3. However, traffic to destinations outside of the internal network is sent to the internet using the default route. This isn't the only way to use a default route, but it's a very common use case. Okay, I added some IP addresses to the diagram, and also configured a couple static routes, which I'm not showing here. I then checked R1's routing table. First, notice the part I've highlighted. Gateway of last resort is not set. This means that no default route has been configured yet. Gateway of last resort is another name for default gateway.
Configure that one.
Now, in R1's routing table, there is a route to 10.0.0.0/8 with R2 as the next hop, and a route to 172.16.0.0/16 with R3 as the next. Perhaps these are networks used internally by the company. Now let's tell R1 to send all other traffic to the internet. Here's how to configure a default route. The structure of the command is the same as any other static route, but the network and net mask should both be all zero, O.O.O.O. That's it. R1 now has a default route. I checked R1's routing table. Let me point out a few things. First, here's the route. O.O.O.O via 203.0.113.2. Notice next to the S code indicating that it's a static route, there is an asterisk. What does that mean? In the code's legend, it says that the asterisk means candidate default. It means this route is a candidate to become the router's default route. It's possible to have multiple candidates. In this case, there's only this one. And here it states, gateway of last resort is 203.0.113.2 to network O.O.O.O. So the route we configured was indeed selected. Okay, that's all we'll cover about default routes for now. The configuration is the same as a regular static route. Just remember that the network address and net mask are both O.O.O.O. We will use default routes in many future lessons as well, so you'll get more familiar with them throughout the. Here's what we covered in this video. We reviewed connected and local routes by looking at the routing tables of R2, R3, and R4. Then we looked at static routes and how to enable PC1 and PC4 to communicate over the network. After that, we configured the static routes necessary for them to communicate. And here I've listed the commands to configure static routes. Usually, I just use the first option, specifying only the next hop IP address. But you should know the other options too. And the final topic was default routes. We looked at default routes earlier in the video when talking about PC1 and PC4's default gateways. And then at the end, we looked at how to configure a default route on a Cisco router. Okay, now let's go to the quiz to test your understanding of what we covered in this video. Here's quiz question 1. Which of the following commands configures a default route on a Cisco router?
Which of the following commands configures a default route on a Cisco router? The answer is default. The answer is A. Route and the IP address.
Pause the video now to select the best answer. Okay, the answer is A. IP route O.O.O.O, O.O.O.O, 10.1.1.255. When configuring a static route on a Cisco router, you cannot specify the prefix length with a slash. You must write out the net mask. So B and D are incorrect. And in a default route, all bits of the net mask should be 0, as in A. So A is correct. In C, the bits are all 1, making it 255.255.255.255. That is not correct. Okay, let's go to question 2. Examine R1's routing table. Which interface will it use to forward packets destined for 8.8.8.8?
Examine R1's routing table. Which interface will it use forward packets destined for 8.8.8. So packets that destined for 8.8.8, you will see are the 8.8.8 configured on the interface. So in this IP address, there are no configuration for 8.8.8.8. So we will see for the routing table the static routes of the remote connection that figure this device are default route. So it forward all the routes the router. The 10.0.0.0/8 IP address, the 172.16.0.0/16, and all the IP address that configured on that router. So it's 12.0, 13.0, and 203.0.10/24. So it will be forward the packets via gigabit Ethernet. So that's to because it's a default route. There are no packets for it. The static routing because on that device.
Pause the video now to think about the answer. Okay, the answer is C, Gigabit Ethernet 02. The only route that matches destination 8.8.8.8 is the default route. This route doesn't specify an interface, but it does state a next hop of 203.0.113.2. So if you look at the route for 203.0.113.0/24, you'll find it's directly connected to G02. So R1 will send packets destined for 8.8.8.8 to next hop 203.0.113.2 using the G02 interface. Okay, let's go to question 3. Examine the network below. Complete the graph with the static routes needed to allow PC1 and PC4 to communicate with each other. Pause the video now to think about the answer.
So for the routing table that will be sending the connection between 192.168.1.0/24 and 192.168.4.0/24, it has to be connected two other ways. So when it's not connected, it will not sending the pings for each other. So for the R1's destination to 192.168.4.0/24, the next hop will be, you can see for the R1's interface, the next hop will be 192.168.13. And it goes through for the R2, so goes wrong or the next hop will be 192.168.12.2/24. For the R2 destination 192.168.1. 0/24 will be 192.168.12.1/24 for the next hop. And for the destination 192.168.4.0/24, the next hop will be um, 192.168.24.4/24. For the R4 destination 192.168.1.0, the next hop will be 192.168.24.2/20.
Okay, let's check. Note that the graph specifies R1, R2, and R4. We're not using the path via R3 this time. So each router in the path needs a route to 192.168.1.0/24 and a route to 4.0/24. R1 has a connected route to 1.0/24. So it just needs this path to 4.0/24 with 192.168.12.2 as a next hop. As for R2, it needs this route to 1.0/24, next hop 12.1, and this route to 4.0/24, next hop 24.4. R4 has a connected route to 4.0/24, so it just needs this route to 1.0/24, next hop 192.168.24.2. Okay, with these routes on R1, R2, and R4, PC1 and PC4 should be able to communicate with each other. Let's go to question 4. Examine the following static route in R1's routing table. What command was used to configure this route?
Examine the following static routes in R1's routing table. What command was used to configure this route? Is directly connected gigabit Ethernet 0/1. Command is the interface exit interface 1. The IP route slash zero. The answer is B.
Pause the video now to think about the answer. Okay, the answer is D. IP route 172.20.0.0, 255.255.0.0, G01. The route states that the network is directly connected, so you might think it's a connected route added automatically by configuring an IP address, as in option B. However, that is wrong for 2 reasons. First, the route has the code S, so it must be a static route. A connected route would have a code of C. And secondly, 172.20.0.0/16 is a network address. You can't configure a network address on an interface, so the IP address command in option B would not work. You configure a static route and specify only the exit interface, as in option D, it appears as directly connected in the routing table. Then a technique called proxy ARP is used to find the next hop. Proxy ARP is beyond the scope of the CCNA, but feel free to Google it if you're curious. Okay, let's go to question 5. Examine the diagram below. How many static routes would you have to configure on R3 for it to know all destination networks? Pause the video now to think about the answer.
2. B2 routes.
Okay, the answer is D, 4 routes.
How many static routes would you have to configure on R3 for it to know? Answer? All other destination.
R3 knows its connected network, 192.168.13.0/24 and 192.168.34.0/24. For it to know all destination networks in this diagram, you would have to configure 4 additional routes: 192.168.1.0/24, 4.0/24, 12.0/24, and 24.0/24. Okay, that's all for the quiz and this video. I hope it was helpful. Thanks for watching. Before finishing this video, let me thank my...
Then we just gonna open up Anki flashcards and go to Dex and go to the day 11 part 2 flashcard study crowding, and it has 13 to do. And study them. Code in the routing table indicates a candidate default route asterisk. Static routes in which you specify only the PRS directly connected in the routing table. Exit interface. Configure a default route, specifying the next hop IP. Specifying the next hop IP. IP, IP route, IP address, subnet mask, next hop. Default route. So it says the default route. Configure static route, specifying exit interface. So the command is IP route, IP address, subnet mask, and exit subnet mask interface. Route, IP address, subnet net mask. The routing table, the output gateway of the last resort is not set means the router haven't configured default route. Configure a static route, specifying the exit interface and next hop IP. IP route, IP address, net mask, exit interface, and the next hop. The route is the least specific route possible. Default route. Configure a static route specifying the next hop IP. IP route, IP address, net mask, next hop. Then send a packet to destination. Does the router need to route to every network in the path to the destination? It only route to the destination. Does the router route path to the destination? And it needs a route to the destination. So the routing table indicates a static route as route is often used to direct traffic to the internet. Default route is route to 0.0.0.0/0 netmask. For an end host like a PC to send packets outside of its local network, it will send the packets to its default gateway. Like this. I have finished the text. If you only specify the exit, router will have to use our proxy for every destination wants to reach. It can be considered worse stick to using the headline. static labs. So
Welcome to Jeremy's IT lab.
I'm gonna search up your CCNA first file that Jeremy puts the drive. We can search for the haven't like video static routes. We can download the script. Um, mm, mm, for the lab static routes. Reload it. Can for this section, I will try to configure it myself without actually seeing the video. Will try to configure it myself. We got a set of instructions here. We got two routers, three routers, and two switches, and two PCs. And it says all devices have now pre-configuration. Step one was configure the PCs and the routers for the network diagram, including all host names, IP address. Remember, you configure the gateway, the PCs. You don't have to configure the switch. You configure static routes and routes to enable PC1 to successfully ping to PC2. So for the PC here, got an IP address to configure to fast Ethernet 0 that have 92.168.1.1. It says before. For the settings, the default gateway is 92.8.1. 254. 254. Okay, we don't configure for the PC1. So for the router one, we can configure CLI. And for the PC1, IP address 1.254 shutdown space. D 0 0 integrate 0.8 12.1 0. 12.1. Okay, no shutdown. What's that? What's name? One. Cross this. We have configured the basic tab for step 1. We're gonna configure on PC2. So PC2, the default gateway into 168 dot 3.25 default gateway. And for the IP address 192.1.3.1 at mask/24. The router we can configure for the CLI. Enable mistype. I have to fast forward because I didn't configure the no IP domain settings or configuration with translating the miss EM for the domain server. Interface G01 IP address 68 dot 3.254 shutdown and G00 address 192.8.13.3 and now shutdown also. We have to configure the hostname R3. So we don't configure the R3. So we can configure for the R3. Host enable config hostname interface G01 IP. Hello. Hello. configure G01. G01. IP address 192.168.13.2 master interface E 00 IP address 192.168. Dot 12 dot 2 dot 0 dot 2. Okay, no shutdown. Then we configure the, okay, already configure the host name, so we continue to start to configure static routes on the router to enable PC1 to successfully ping PC2. So in this step or section, we have to configure the static routes on each router. So we can start at the router 1. So for the destination, to the static routes that will be a destination, it will be 192.168.1.0/24 and 192.168.3.1/24. So we have to configure static routes to those IP. So in here we can continue on configuring the static routes on R1. Okay, so the command is conf IP route for the 192.168 dot 1 .1.1 for the destination of PC1 destination. IP route 192.168.1.1 0 for the net mask, and the next hop for the route 1.1 is already reachable. So we will configure the routes, PC2 routes 168.3.1 for this section. We have to configure it. 255.255.255.0, and for the next hop is 192.168.12.2. I'm using the next hop IP, not the exit interface. Okay. Is inconsistent address and consistent address and 168/24. Consistent press masks is why we add inconsistent address and mask errors occurs when the IP address you specify for the destination network is actually a host address. Cisco routers require destination address to be a network-based address. Okay, so what's wrong? So this IP address, the destination IP address, has to be the network address. Okay. So we already configured IP routes for the PC2 IP address. Then we can see the configuration to show IP route. The static 3.0/24 via 192.168.12.2. Okay. And I configured IP address for the default gateway for the PCs and the IP address for G00. So dot 254 for the local and 12.1 is 12.1 for the G00. So the configuration is set. We will move for the R2 IP route configuration. So as you can see here, we will configure destination routes for the 192.168.1.0/24 for the PC1 and the destination IP 192.168.3.0/24. The PC2 destination I will configure the command IP route 192.168.1.0.255.255.255.0. It goes through G00 R1's interface, so the IP address is 192.168.12.1. Okay, and it worked. IP route for the 3.0, it's gonna pass for the exit interface IP. Next hop IP G00 R3's interface. So the IP address is 13.3. Yes. Okay, we already configured IP routes R2, and we can configure IP routes on to enable config route. So as you can see here, I'm gonna show you. Do show the route. Okay. We already configured according to our configuration earlier. we have configured on G01 interface. For the IP address of that interface is 192.168.3.254. So it's in the local connected. Right here. Okay, and for the G00 interface that has 192.168.13.3/32 is the local, and connected is the network portion or network address of its IP. So the 192.168.3.0/24 has already configured and directly connected to PC1. So it means we the last we configure is a route to 192.168.1.0/24. We already configured for the PC2 IP address. So the syntax IP route 192.168.1.0.255.255.255.0, and the route will be to R2 G01 interface that has IP address 192.168.13.2. Hit enter. Do show IP route. So it static. We have 192.168.13.2. Okay. When we show IP route configuration, you can see the static configure that we do earlier that has too simple. We have to see to static configuration. It means the configuration that we do is working. As you can see, static configuration is successful. It's true, but we have to check it. Check all the routes. We have to check all the routes successfully for PC1 to PC2 with the ping command. And now we will have to ping PC1 to PC2. So what I'm gonna do is I am gonna ping this PC1 to PC2 to see our configuration is working or not. We can do terminal here. Match this first command prompt. Let's ping 192.168.3.1. Okay, as you can see, the ping is working because it replies from 192.168.3.1 with the byte 32 bytes and 1 millisecond of time and time to live. 125. The packet sent is 4, received 4, lost 3. What will be the issue or the cause for this issue? I mean, because the routers will have to send the ARP request and ARP reply for the first time. That's why these 3 requests is timed out, because it tries to, when it tries, it got the RTO or request time out, and when it tries, it fails, try it fails, try it fails. When he try the 4th time, it will be successful. So we can try to ping it once again and see. So as you can see here, the ping is successful from the PC1 and PC2. The communication and the static routes went to 2 connection, 2 endpoints are successful. That's why we can ping. And when I want to ping from PC2 to PC1, it will be working again without the RTO or request timeout. Let's try ping 192.168.1. As you can see, the ping is working. So we already resolved and received the 2 communication between PC1 and PC2. That's why we can configure this app, and that's why we can successfully communicate those PC1 and PC2. We can save. Now we will watch Jeremy's videos.
This is a brief course for the C.
You can fast forward.
Start on PC1. Click on config. And the first thing we should configure is the gateway here. This is the address to which PC1 will forward packets, which are destined for a location outside. PC1's gateway is R1. I'll put in R1's IP address, 92.168.1. Next, click on Fast Ethernet 0, which is PC1 networking, and type in the IP address here. Automatically fills it, digs, post configure the description to switch 1. G02.168.1.255.255.255.1. The description. So IP G01 is up. G00 is up there. Not a problem. It's just because R2's G00 interface is still shut. Go on R2. On R2. I'll do the same as I'll just go on R2 postal, but the rest looks okay. Enter 5 big to take that good way reply. Take that freedom. Have to be in global. Let's use the prefix, meaning the net contact 255. Since it's Next, we can if I use context for this route, it means we can generate indicated by the IP route. Go down here. Okay, there is another possible option. Distance metric for this route. Talk about this option in a later video. So, there's the static route we configured, as indicated by the S here, route. There's the static route we configured, as indicated by the S here. You can also see the configured and local routes for R1's two interfaces. Remember, the local route is the actual address configured on the interface, and the /hood is the route to 192.168.1. To practice the other option, I'll point-to-point interface. However, this is a point-to-point, and it connects only to one other device. This is different than, for example, many routers connected to a single switch, which we would call a shared segment. Anyway, don't worry about that for now. 192.168. This time, let's do the next top IP address. 192.168.13.3. Okay, let's check the routing table. Do show IP route, each interface. Let's see. Right, exit.168.168.13. Do show a connected and local route. Okay, looks like PC1 is able to reach PC2. Configured. Subscribe to the channel. Okay, like PC3. Let's go on PC1 and try out Prog. Address if we configured everything correctly. PC2 is able to reach PC1 with that. Like the video. If you want to leave a tip, check the links in the description.
Okay, yeah, I think that's it for this session. I will be bringing again at 8 p.m. Gonna take a bath and eating for this time. I'll see you in the video.